I'm going to show now how to run SmartGeo for the optimization example. So once all the layers here into the Argus 1 project are filled up, with the grid layer active we can select PIEs, run SmartGeo. We need to select the working directory and start filling this form. In the PSO parameters, we can find a list of all the parameters that can be estimated with a SmartGeo. And in order to obtain the calibration of the parameter, we need to check to activate the calibrate option. These first four parameters are the pilot point hydraulic conductivity values, and their range of variability are directly inferred from the Argus 1 project. The tolerance are values which are utilized for stopping as a stopping criteria only if the stop control option is selected. In the value column, we can assign to each parameter the initial value of tentative. But if we select the option random initial value, we don't need to define the value field, because the initial value is generated randomly. In this case, we also want to calibrate the mean of the logarithm of the hydraulic conductivity, and we need to specify the lower and upper limit. And we activated the random initial value. We decide to calibrate also the variance of the logarithm of key, the logarithm of the specific storage, which is a constant value for all the domain, and also the integral scales of the hydraulic conductivity field along the x and y direction. The range of variability for the variance is 0, 1, of the specific storage is -10, -7, and the integral scales are 110 and 110. Okay, the effective porosity is not calibrated because it's not utilized in this case because it is a confined aquifer. SmartGeo performs in the inverse problem many runs of MATFlow for looking for the optimal values of the unknown parameters, which minimize a fitness function. The fitness function is described here in the user guide file. The minimum of the fitness function is searched through the use of an optimization method called PSO. The PSO parameters can be modified here, and in particular the user needs to modify the number of bees and the number of iterations, which are parameters which influence the number of MATFlow runs utilized for finding the solution. In particular, by increasing the number of the bees, increases the efficiency of the PSO in finding the global best solution, but to the detriment of the computational time. In this case, we set 6. And here we need to define a number of iterations, which are 1000 in this case. Here we need to define the kriging parameters. In particular, the x and the y are the grid cell size, and they shouldn't be too small for not increasing too much the computational time. We need to define the shape of the covariance function and the number of Monte Carlo simulations, and also a seed number. We need also to set the MATFlow parameters, which are the initial head conditions, constant 20 meters, and we decide to activate this option in order to save and visualize the hydraulic head simulated in all domain. And we need to set the stress period parameters. which are the initial simulation time, the final time, 5 hours, the number of time steps, 5, and the multiplication factor, and the simulation type, which is transient. Here we define the geometry of the layer, and we write minus 10, minus 40, and these are other material parameters that should be checked and filled. Okay, before running the simulation, we need always to save the settings in a TXT file, and then we can run the SmartGeo simulations. This kind of simulations takes a while for running, and the computational time depends also on your computer performance. So we can look directly through the outputs of the simulations, and this is our true synthetic hydraulic conductivity field. And these are two examples of Monte Carlo simulations. Here the first example and the second example. So the SmartGeo is able to detect the high hydraulic conductivity zone in the upper left part of the domain, and the lower hydraulic conductivity zone in this part of the domain. In the help system, we can find also an example of hydraulic conductivity field obtained considering for the inversion only the head data collected in the scenario test 1. So here we have less hydraulic head data to invert. So the representation of the actual field is poorer than before, but the model is still able to detect the high hydraulic conductivity zone here and low hydraulic conductivity zone here, like in the true field considered. So in the working directory at the end of the simulation we can find also files called HSIM001, which is the number of the Monte Carlo simulation, where we can find for each scenario and for each observing well the time, the simulated head values and the observed head values. We can find also a file called BestPar, the number of the Monte Carlo, with the list of the estimated parameters, and we can find also a file called Swarm Ray and the number of the Monte Carlo, which should always be checked, because in the first column we have the number of iteration, and in the second column we have the swarm radius, which is the convergence index, and it should have a decreasing trend converging to a small value. Okay, that's all. Thank you for your attention. Bye.